Hello, this is Horner again, and we are going to take a look at energy F3. You have a spring. Force constant K is set into a hole. Uh-oh, that makes a problem. In a table, and a light platform is attached to the top, so we don't have to worry about the mass of the platform. The spring extends a distance d out of the table's hole, out of that surface, and a mass is set on the platform. When you set it on there, it is now flush. They say that when the mass is released, the mass is projected directly up into the air and it reaches a maximum height of 4D. One thing that I want you to see right off the bat on this one is the following. Notice that, here I'm going to grab my pen, this distance from here to here is actually 3D. This is 4D, but 4D goes all the way down to the surface of the table. So what do? We took 4D minus a D, and that gives me a total travel distance here of 3D. That will be important later. Next thing they want us to do is write an expression for D in terms of mg and k. So those are the only things that we can have other than constants or halves or things like that. So we know that when it's compressed, it's got spring energy. And so here we go again. The energy in a spring is equal to 1/2 kx squared. And we know that at the top, it's got potential energy. So potential energy due to gravity. Down at the bottom, we have potential energy due to the spring. And so potential energy due to gravity. That too looks terrible. What am I thinking? Oops, now I'm really not thinking. All right, here we go. So let's get rid of this. There we go, that's much better. And we're going to put in x here squared. Now we're talking, and this is mg, but notice we don't want to use L, we want to use D. So here we're going to put in mgd. So let's go ahead and let's plug everything in and get a good equation here. Notice that we do compress by a distance d. So instead of x, we're going to get rid of that x, and we're going to say that that is d squared. And then this d is not just d, it's got to be 4 times d. So we're going to get rid of that, and we're going to put 4 times d. So now our equations become 1/2 k d squared, and we become 4 mg times d. And the 4 comes from the d, but we just went ahead and put it out front. Let's go through and set the two things equal to each other. So this is 1/2 k d squared is equal to 4 mgd. We're going to notice that the only thing that's going to cross off is one of the d's. So we're going to get rid of that d, and we're going to get rid of the square. And we need to now solve for d. So to solve for d, we're going to multiply both sides by 2. When you do that, you get 8. The m and the g are fine, but we need to put the k on the bottom, and that is where that comes from. If you do all that, you get 2 points. So 2 points altogether. The first point was just getting an equation like this, and then the second point is for actually going through and getting the expression in terms of d. So if you just do this, you've not really done enough. You really got to move on. Cool, so let's move on to the next part. Let's look at part B. So the way that the pagination, or however the pages came out, didn't come out real well, so I'm going to kind of put it like this. From the instant the mass is released until it reaches that highest height, the mechanical of the mass, Earth, spring system is E. So this is taking into account that the table serves as the 0 point for gravitational potential energy. So all that means is that if we're measuring heights here, this is 0 meters, and then this would be whatever the top one is. So D, if we said D was 1 meter here, then this entire thing up top would be 4 meters. Okay, but they didn't give us anything specific, so we're going to be careful there. They did give it to us in terms of D. So if I want the potential energy due to gravity, I know here it's 0, and I know up here it is 4D. So use a ruler. Don't do what I do. Make sure you use a ruler, and you want to make that's pretty straight. That's your straight line. For the potential energy of the spring, when you do this, notice that your energy is going to be really big when it's totally compressed, and then at D, you don't get any more energy out of the spring, but it's important for you to go ahead and extend that line all the way across. Okay, so that is the one that you see there. And then this is the tough one. This is the one where you have kinetic energy. And if we scroll back up, you're going to notice that the kinetic energy does start. Okay, the kinetic energy does start. And if you come back here, it does start here at 0 because there isn't any. But then you do get kinetic energy at the instant that it starts to move up. Now, we're going to ignore some of that, and we're going to say that you have maximum kinetic energy right here. Okay? At the top, you have minimum. So the graph that you're going to get here is going to look like this. So let's move it down. We are going to get some energy here, and it's going to gradually get bigger. Oh shoot, that's not real good. Here, let's try that again. That energy, oh no, I don't know what I did. New tablet, sorry guys, I'll get it figured out and it'll work better. But we need to erase this. I keep hitting the button and that makes it scroll. So I'm going to get rid of this. Here we go, we're back. And as that spring pushes it up, it gets more and more energy until it comes up to here. Once it hits 3/4, then it's got all the energy it can have. Okay, why is that? Well, that's because if you go back up here, notice it's only traveling 3D. So the most potential energy you're going to have is above where that block is released. So you lose 1/4 of that energy that we would have said you had if it would have launched at the bottom. That's the trick to this one. And then this line should go straight down to 4D. So this should be, I know that's terrible. I need a ruler. This should be a straight line that goes straight down here. And then this one kind of progressively kind of comes up to here. So anyway, that's similar to what it looks like. This is worth 6 points. Okay, so let's go through each and every single one of the points because I think that's super important. If you want to follow along on your rubric, you can do that. So this graph is 2 points. You have to go through the origin. That's the first point. Okay, it needs to pass through this point and this point. That's your other point. Okay, it really should be a straight line. If it isn't a perfectly straight line, they're going to give you a little grace there, but it should not be some funky curve. For US versus Y, it should pass through the point 0E, okay, D0, and 4D0. If it does all three of those, you get a single point. This should be a continuous upward opening parabola between 0 and D. So really, I think I probably need to go back and draw this one a little bit better. So let's get rid of this. And it should be a somewhat opening parabola. So really it's a little easier to draw that if you start here and then kind of come up. So it should look like that. It's just really hard to draw on this little tiny picture. So on the AP test, they'd probably go through and they would make it a little easier to do. I'm going to try it again here. So I'm going to go down a little bit. Oh shoot, it's just really hard to draw with this. I'm so sorry. It should kind of open up a little bit. You can kind of look at the key that you have, but I'm going to try it one more time, and if it works, great, and if not, well, we'll chuck it up to experience. So I'm going to have this kind of come down, and then it should curve like that. Okay, so best I can do with this new pen, and that's what it should look like. So that is your second point is, oops, your second point right there is this should kind of have a curve like that. The next one is this one. You should pass through here, here, and here. That's 1 point. And then this should be a downward opening parabola right here. So let's make it a downward opening parabola so you're not super confused. And we'll make this one more of a straight line. So here we go. So this one should start about right here. And then it should come up. And it should be more of a parabola like that. And then this should be a very straight line all the way down. Okay, So best I can do with what I've got, but that open parabola kind of pointing down is here. This one you'll see is pointing up. So you could think of that as a smiley face, and you could think of this one as, when we've talked about curves, we could think of that one as a frowny face right there. So not real easy to do digitally. Really sorry about that. Let's go ahead and go to the next point, the next part, because it is the next 4 points. So the spring is reset so that the length 3D of the spring extends above the table. Okay, a new mass is set on the spring's platform, and the spring again is compressed till the platform is the same level. So before the mass is released, the student makes the following prediction. It says the spring will have 3 times more energy, but the mass is 3 times as much. It should take 3 times as much energy to raise triple the mass, so the mass in the new situation should reach the maximum height that the other mass reached before. Okay, so they reset it. Notice that this spring is now above the table. What in the world do they mean by that? Here, I'll show you. They've taken this spring, it's D, D would be here, and D would be here, and they've put it now, instead of down in the hole, they've put that spring so that it's like this, it's above. And this distance is 3D. But on top of that, they put a mass on here that is 3m. So it compresses down 3D, but it also has a mass of 3m. So what they're saying is, or what the student says, is that it takes 3 times as much energy to raise, so the new mass should reach the same maximum height as the other one did before. Okay, the student is correct in that the energy raises a triple mass to the same height. So here we just need to say same height is correct. Alrighty, and that's because triple the energy of the spring should make it go up to triple the height. Okay, the student is wrong, saying that if you triple the spring compression, that will triple the initial energy. So this is not correct. Okay, not correct that if you triple, so 3 times the compression, so we said 3 times D, you will get 3 times the energy. So that is not equal. So US is not going to be 3 times. Okay, if you triple the spring compression, then what will really happen is your US will be equal to 1/2. Remember, it's K times your distance that you've compressed it squared. So that will make, instead of 3, you're going to increase. So when you have 3 times the distance, then that's 3 squared, and that will be 9 times the potential energy of the spring. Okay, and because of that, when you go back up, triple the energy raises a triple mass to the same height. We said that that was correct. Okay, but here, down here, we have 9 times the energy. And because you have 9 times that spring energy and you have 3 times the mass, then your height will go up, will result in 3 times the height. Okay, and that's equal to, and really we can say that because mu g is equal to mg times the height that you go, which is y. So 9, we'll say it one more time, 9 times the energy and 3 times the mass results in 3 times the height. So you won't go to the same height, you would go higher. So same height, this would be higher, and it will go up 3 times the height because of it. So hopefully that makes sense, and that is the end of this problem.